We're going to be talking about the derivative. And again, as we kind of get into this unit on derivatives, you're going to see that we're going to start with very, very formal definitions and work that we're doing to find the derivative. And as we move into lessons later on in this unit, you'll find we're going to use some rules and quicker ways to solve these to get into the important stuff, which is the applications of actually being able to take the derivative of a function. So again, as I said, we're going to be using a little bit longer methods to do this. So we're going to be focusing on using this equation right here to find the derivative of a function. All right. And for the notation purposes, you'll see the letter F with that little symbol up to the kind of looks like it's in an exponent, but it's not. It means F prime. So whenever you see that little symbol there, that means you're finding the derivative of the F function. Okay, so we're going to talk about what makes a function differentiable at A, what makes it differentiable on like a set of values, but ultimately we're going to be focusing on using this equation, the limit as h approaches 0 of f of x plus h minus f of x over h. And we practiced with this before, so this is really kind of taking older lessons and kind of putting it together. Okay, so if you ever have any issues with this, you can always go back to the very first lesson in chapter 2. Right, that unit on limits actually started with an introduction to calculus lesson. And as I said, this whole idea of finding the derivative comes from the idea of finding the slope of the line, right? The slope of the line that's tangent to a function at a point, right? Everything that we do is from that kind of basic idea. Okay, so let's first start by taking the derivative of this function, the square root of x. Okay, so again, when you see this on the AP exam, right, you won't see this simple of a problem, but at some point soon in the near future, you're going to look at this and be like, boom, I know the derivative. Like I've obviously taken calculus, so I know that the derivative of this, I know the answer already in 5 seconds. We're not there yet, right? We're kind of just beginning to crawl, so we can't really start running yet. So I'm going to use this equation, f prime of x. I'll write it down closer to the slide. We have f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Again, we've kind of used this before, but just a reminder to copy it down closer to the slide if you need it. Okay? All right, so we're going to plug in. We have this is equal to the limit as h approaches 0 of, we're going to have the square root of x plus h, right? We're replacing x with x plus h minus square root of x over h. All right, now if I try to evaluate this limit like we did on our test with limits recently, you would find that you would get 0 in the denominator. So that's a problem. So we're going to multiply, essentially, your understanding of multiply by a conjugate. So I'm going to multiply the top and bottom times the square root of x plus h plus the square root of x. All right, you're going to see by doing this, I'm going to make my numerator a little simpler. All right, don't actually distribute the denominator. So the limit as h approaches 0. So watch what happens in the numerator. When you multiply radicals, you guys know from your experience that the radical symbols will go away. So that means you just have x plus h, right? And then the middle term is going to cross out here. Remember, when you multiply conjugates, you know the middle piece is going to be 0. So negative square root of x times a positive square root of x is minus x. Again, don't actually distribute the bottom. Just multiply it with your parentheses. Okay, now the numerator, you're going to see x minus x goes to 0. So now the numerator is just going to be that h. All right, so we have f prime of x equals the limit as h approaches 0 of h over h times this conjugate piece from earlier. The h's are going to cross out. So that's going to leave us with f prime of x equals the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. Okay? And now we can plug in 0 for h, right? Similar to what we would have done in the last chapter test, right? Once we actually have our issues of dividing by 0 out of the way, we can go ahead and plug in. So we're going to plug in and get 1 over the square root of x plus 0 plus the square root of x, all right? And x plus 0 is just going to be x. So that's 1 over the square root of x plus the square root of x, which is 1 over 2 times the square root of x. So this right here is the derivative, all right? And, again, not to make you upset, but once you get farther in this course, you're going to see that this problem will take you probably 1/10 of the time to do. Okay, let's move on to the next one. We're going to use that same formula again, all right? F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. It's one of those things that, I know you're like, well, Mr. Franger, you have the formula right above you. It's good for me, good practice for me, and good practice for you to write it over and over again, because it's something that you're going to need to have, and I'm not going to give you this formula. So it's good practice to keep writing it over and over again. Now, to help myself with the work here, or more space, I should say, I'm not going to write the f prime of x equals the limit as h approaches 0 step over and over again like I did over here. I mean, technically you should, but I know I'm going to have to do some algebra. So I'm going to do the algebra, and then once I'm ready to actually evaluate the limit, then I'll bring down all the notation. Okay? So I'm just going to focus on this piece to start. So I'm going to write x plus, let's go all the way up, x plus h squared minus 2 times x plus h minus x squared minus 2x all over h. Okay, so I'm going to deal with the numerator. We have a binomial squared, so I'm going to expand that. Hopefully you're ready or confident in expanding this. So x squared plus 2xh plus h squared minus 2x minus 2h minus x squared plus 2x all over h. All right, so let's see what crosses out here. I have x squared minus x squared, right? X squared minus x squared is going to cross out. Looks like the 2xh is still going to be around. And then plus h squared, I guess I can write that first. So h squared plus 2xh. And then the minus 2x and the plus 2x is going to make 0. So that's good. So the only thing I need to write is minus 2h all over h. Let's factor out an h in the numerator. We'll go this way. So h times h plus 2x minus 2 all over h, and that crosses out. So now we're ready. So f prime of x equals the limit as h approaches 0 of, here's my simplified work here, of h plus 2x minus 2. Oops. Okay, and now I can plug in 0 for h. If you plug in 0 for h, you just get 2x minus 2. Okay, so that's the derivative of x squared minus 2x. All right, let's keep going. Now, the next part of this lesson is to get some experience looking at the graphs of the original function and using characteristics of the graph of the original function to try to graph the derivative. All right, this can be a little tricky. We are going to look at a Desmos activity. It's going to kind of try to help us understand this a little bit more. The key thing I want you to know is that when we do example 3.13, that you're always just focused on how they are getting those values. It doesn't need to be like an exact science, but I just want your brain to understand of like why they are drawing the sketch of the derivative, where they're drawing it. Okay. Now, before we do that, a couple of notation pieces. Right here are all the different ways that you can express the notation for the derivative. We've already done f prime of x. There's the other notation, the most common one. All right, this Leibniz notation from a mathematician about 300 years ago is dy dx. You can say dy over dx, but mathematicians say dy dx. And then there's y prime. And then the other one, which is a little very similar to what we said with the dy dx, is the d over dx. And I'll explain to you kind of how I approach those or when I see those in problems of what there's like just a little bit of a difference in when I see them and what I'm thinking they're telling me. Okay, so let's go to this one. My blue curve is the original f of x function, and it wants me to sketch, I'll use orange, wants me to sketch the graph of the derivative. Again, this is a very difficult process, so I want you to understand that. Just do your best to understand, go through the learning process, and as you like mess up and kind of take in the feedback, you'll start to get better at this. Excuse me. Ooh, man. Excuse me. Okay. So the first thing I want you to look at when you're looking at the original curve is, for reading from left to right, you'll notice that the first piece is decreasing. Okay. So when you're decreasing, that means if I were to draw lines that are tangent to this blue function at any point as I'm beginning, all of my slopes will be negative. Right? I'll just draw one, for example. Right? If I draw a tangent line right there, has a negative slope. So whenever you see your original function is decreasing, right, as you're moving from left to right, you know you need to be in the negatives. So I know I need to be somewhere in the negatives. Now, the reason that I'm drawing it like this is because you'll notice that as I'm decreasing, I'm not decreasing as fast as I move towards this -2 function, or sorry, this -2 x value. So my slope is getting less and less steep, which means I'm getting less and less negative. So really, I'm just getting to this place at -2. Now, the reason -2 is important, I'll use a different color, but the reason -2 is important is because, or I guess just by -2, you'll notice that the line that's tangent to the point around x equals -2 is a horizontal line. All right, and that has a slope of 0. So I should see, right? I should see when we get to around -2, I should see an x-intercept if I'm sketching this derivative function in orange. Okay, now once you move past that x value of -2, you'll notice that we're actually starting to increase. Okay, so we're increasing. So it means we have positive values here. So positive values, right? And then I'm kind of rounding it out because you'll notice we're increasing not as steep or not as steeply. That probably doesn't, grammatically that's wrong, but you can see we're not increasing at a rate as quickly. So our slope is getting a little bit less. And then same kind of deal. Oh, I should have come back down. I'm sorry about that. As we get here, we're kind of coming back down because our slope should be getting smaller as we get up to like these pieces, right? So we're getting a less steep slope until we get to this x value of 3, and kind of like before, right? Right there. Where'd you go? I need to have a color. There we go. You'll see the same thing where at x equals 3, we have a horizontal tangent line, okay? So that means we're going to have another x-intercept at 3, okay? And now we're decreasing again until we're finished. So something around like this. All right, again, that's not, my sketch is not perfect, but I want you just to kind of take away from this is that you're focused on increasing and decreasing in the original, as well as where you have those relative maximum and minimum values, because that's going to give you those zeros for the derivative. And we'll practice on Desmos as well. Okay, let's keep going. Now, one thing that we're going to talk about before we do this next example is about differentiability and in the implication of continuity. All right, so if we have f of x is a function, and we have a value a is in its domain, and that our function f of x is differentiable at a, so you're able to take the derivative at that point, then your function is continuous at a. I want to make sure you understand then the very first point in this summary is that the opposite of that is not necessarily true. Okay, so make sure you understand the direction that we're, like the way that you can say this, and going the other way is not necessarily going to be true. So just be careful there. This is a good reminder to go in and read the textbook that I post. You can read the section on derivatives and continuity from lesson 3.2. You can also go to Calculus for Dummies. I posted that already. You can check it out. It's a lot of pages for derivatives, which makes sense, right? This is one of the key questions in calculus, finding the slope of the line that's tangent to your function at a point, right? So it's going to be a lot. But what's nice is that the Calculus for Dummies that I uploaded for this chapter will be the same that I upload for the next chapter. So yes, it is a lot, but you can space it out over, these next 2 chapters on derivatives are going to take us until Christmas. All right, so we have a lot of work we have to do on derivatives. Now, what I'm going to focus on is this idea of the fourth one here, that it may fail to be a little more complicated. In the book, it shows you, we kind of did one like this early on in the class, where as you approach 0, you'll notice that you don't really have a value that you're approaching from the left and the right. So it can be a little bit tricky if you get any of those. All right, so let me show you this problem. And this one's going to be a little, this is one of those application ones. So it's going to take us a little time. It's going to be a lot of work. And you'll notice it even has a second slide continued. So there's a lot of work that needs to be done here. But you guys have more space. So make sure you're using your space where you need to. Okay, so we have a toy company wants to design a track for a toy car that starts out along a parabolic curve and then converts to a straight line. So they're giving us the function. It is a piecewise function. And our x value that we kind of see where it switches is at -10. For the car to move smoothly along the track, the function must be continuous and differentiable at -10. So we're going to find values for b and c that makes this true. All right, so here's a little graphic of what it needs to look like. Now, again, you could just guess and check this, right? You have Desmos, you know how to do piecewise functions, and you could make B and C sliders and start sliding them around until they link. But I'm going to show you the algebra of how to do it. All right. And ultimately, it's going to kind of help you understand this idea of continuous and differentiable. Okay. Okay, so for this to work, the first thing I'm going to do is I'm going to make sure that the function is continuous. Okay. So the first thing I'm going to do is, in order for it to be continuous, so for this to be continuous, continuous at x equals -10, the limit as x approaches -10 of the function must be the same as when I plug it in. Okay, so when I'm looking at this and plugging it in, and in order for this to be equal, right, for it to be continuous at negative, for that to work, all right, what I need to make sure to do is look at it from the left as well as from the right. Okay, so essentially what I'm saying is, for this to, like in Desmos, for them to connect, since I'm not plugging -10 into the function that's the left piece, if I look at the limit as the function, or at limit as x approaches -10 from the left, then if that equals to when I plug in -10 to the function, which is the right piece, if those are the same, then I know that this will be continuous. So the first thing I'm going to do is plug in -10 into my left piece. Okay, so writing down my left piece, I have 1/10 times, so 1/10 times -10 squared plus b times -10 plus c, and that has to equal to f of -10, which is really plugging in -10 to the other piece. So -1/4 times -10 plus 5/2. Okay, so let's do a little algebra here. We have negative 10 squared, which is 100. 100 divided by 10 is 10. This becomes minus 10b plus c. And on the right side, we're going to have a positive 10 fourths plus 5 halves, which can be written also as positive 5 halves plus 5 halves. So 2.5 plus 2.5 is 5. Okay, so ultimately, when I look at this here, this is what happens when you have the left on the right equal to each other. I'm going to clean it up just a little bit. I'm going to move the 10 to the other side to have negative 10b plus c equals 5 minus 10 is negative 5. And I'm actually going to solve for c. All right. Make sure that's what I want to do. Okay, so solving for c means that I'm going to have positive 10b minus 5. Okay, so this is kind of the first thing to make sure that it's continuous, and before we get into that it's differentiable. Okay, now if it's differentiable, all right, when I look at finding a derivative from the left side and the right side, they must be the same, right, to match. So ultimately, okay, so if I were to look at, let me kind of just show you where a little bit of a breaking point here. And again, please utilize your space. I did not give enough room, but with the extra space, you should be fine. So if this is going to be differentiable, so differentiable at x equals negative 10, right? Then f prime of negative 10 is going to be the change in the y over the change in the x. So the f of x minus f of negative 10 over x minus negative 10. Okay, but here's the deal, guys. Because this is a piecewise function, we have two ways we have to evaluate this derivative. We have to evaluate it from the left and from the right. So we have to use both pieces. So we have to do two pieces of work here. The first one is that I'm going to be looking at, so we have to, I forgot to put in here real quick. Let me give you some more space. So f prime of negative 10, I forgot to do the limit as x approaches negative 10, right? If this is going to be true, it would be much simpler if we had one piece. We have two pieces, so we have to do it from the left side and the right side. So I'll start with the left side, is the limit as x approaches negative 10 from the left. All right, I'm going to use the left piece, which is that 1/10 x squared plus bx plus c. So 1/10 x squared plus bx plus c minus f of negative 10, which we already did earlier, which is positive 5, all over x plus 10, right? Minus the negative 10 is positive 10. Now, if I plug in, right, if I use what I found at the very beginning about the continuous piece, if I plug in 10b minus 5 for c, right, for that letter c, make this a little simpler. So I have 1/10 times x squared plus bx, and then this is going to be plus 10b minus 5 minus 5. All right, all over x plus 10. Okay, now what I'm going to do is I'm going to essentially I'm going to be multiplying the top and bottom here by 10 because I have this 1/10 in front of x squared. I think it'll be a little simpler if I go ahead and multiply the top and bottom by 10. Again, it's not changing the problem, right? 10 over 10 is 1, but it'll make it a little nicer. So let me show you my process here. So that's going to just become x squared plus 10bx plus 100b, and then see if you can follow along here. We have negative 5 and a negative 5, which is negative 10 times 10 is minus 100. Okay, all over x plus 10. Now, in the example, right, I keep pausing this. You probably noticed, like, whoa, he's like not finishing sentences, right? I'm trying to get this right using the textbook that we're using. And it says here to factor by grouping, but I can't think of a way, maybe I just did, to get to like show you how we would do factor by grouping. Like I can show you the factors that you're supposed to use in kind of a simple way or maybe a uncomplicated way to write it down, but I'm trying to figure out a way to actually get to the factors that they want because there's not really a way to do this the normal way of factoring by grouping. So what I've kind of looked at in looking at this problem is you've got the difference of two squares here,
x squared minus 100, but you have a middle piece. So essentially what you're going to do is you're going to have the x plus 10, the x minus 10, but you're going to have another piece left over with that b, all right, with that 10b to get to 100b. So I'll go and write down the factors. So I'll write down the factors, but hopefully when we're doing this in person, I'll have figured out like the way to explain it besides just writing x plus 10, x minus 10 for the difference of two squares, but then writing also plus 10b, because that will, all that multiplying out will give you that numerator. Again, I should have made sure to put times 10 right here because I did multiply the top and bottom by 10. So now the x plus 10s are going to cross out. So now we have the limit as x approaches negative 10 from the left of x minus 10 plus 10b over 10. All right, so if we go ahead and plug in now, we have negative 10 minus 10 plus 10b over 10, which is going to be 10b minus 20 over 10. Divide everything by 10, and you get b minus 2. So that's kind of the thing I want you to have right now. Again, you've got a little bit more room than I do, but hopefully you have that b minus 2 for doing this process as x approaches negative 10 from the left, because we're about to do it as x approaches negative 10 from the right. I'll definitely get more room before I do this in person. So I'm going to do the same thing. The limit as x approaches negative 10, but this time from the right, of f of x minus f of negative 10 over x minus negative 10. But this time I'm using the piece on the right. It should be a little quicker because I don't have any unknowns. Negative 1/4 x plus 5 halves. So I have negative 1/4 x plus 5 halves minus 5 all over x plus 10. Okay. Now, when you look at this one, I'm going to go ahead and I want to get rid of that 4 in the denominator. So I'm going to multiply everything top and bottom by 4, so 4 over 4. When I do that, it's going to be negative x, and then if I multiply 5 halves times 4, that's 10, and then negative 5 times 4 is minus 20. Again, leave that alone. Don't distribute it. So that gives you negative x minus 10, and you might be thinking, oh, well, I can't factor, but in the numerator, I can factor out a negative. That gives me x plus 10. So now I can cross that out, and I just have the negative 1/4. And when we talked about limits at the very beginning, if you have the limit as x approaches anything of a constant, then that's always just going to be equal to a constant. Okay? So if this is going to be true, then negative 1/4 and b minus 2 have to be equal to each other. So we're almost finished here, right? I know these must be equal, right? As we approach the left and the right, if they don't match up, then we're not going to be able to have a limit, so it won't be differentiable. So let's go ahead and kind of do the next step here, which is b minus 2 equals negative 1/4. So b is equal to, if you add 2, that's 4/4. So it's going to be equal to, oh, it's not 4/4, Douglas. It's 8/4. My bad. So negative 1/4 plus 8/4 is going to be 7/4. Okay. So it said that, remember, I know it feels like forever since we started this problem. I apologize. But we found B. We just need to find C. And finding that, we're going to use this original one that we found up here. That C is equal to 10 times B minus 5. So C equals 10B minus 5. Let's plug it in. 10 times 7/4 minus 5. So 10 times 7/4. Let's see. Let's go ahead and reduce that. That's going to be 35 halves minus 5. So if we get a common denominator, 35 halves minus 10 halves is going to be 25 halves, which is, if you want to do a decimal, that's going to be 12 and a half. Okay, thank you for bearing with me on that one. That one is extremely tricky. A lot of steps to do there, but ultimately, hopefully you saw a little bit into the insight of how to make sure things are continuous and differentiable. Now let's move into our last piece, which is about higher order derivatives. So we're just going to kind of do the tip of the iceberg here, but we're starting to talk about how to find the derivative of a function, and you can actually keep going, second derivative, third derivative, fourth derivative. So there's no reason to stop. What you're going to see, the kind of the immediate application here is that if you have a position function for an object, finding the first derivative, that function is showing you the velocity, and then finding the derivative of the velocity function or the second derivative of the original position function gives you the acceleration. So that's kind of the most basic application of these higher order derivatives. So let's find the first derivative for this one, and then we'll find the second derivative. We're going to use the same work we did earlier, which is the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, so I'll go ahead and plug that in. That's 2 times x plus h squared minus 3 times x plus h plus 1 minus the original function, 2x squared minus 3x plus 1 all over h. Remember, this is equal to the derivative, the first derivative, I should say, f prime of x. We're trying to find f double prime of x. Okay, so let's go ahead and ignore the notation and just do some algebra. So that's going to be 2 times x squared plus 2xh plus h squared minus 3x minus 3h plus 1 minus 2x squared plus 3x minus 1. So let's go ahead and distribute that 2x squared plus 4xh plus 2h squared minus 3x minus 3h plus 1 minus 2x squared plus 3x minus 1 all over h. Okay, let's get some like terms going here. So we've got 2x squared minus 2x squared is going to cross out. So boom. We're going to have minus 3x plus 3x crosses out. 1 minus 1 crosses out. So I'm going to bring down the stuff I didn't cross out. 2h squared plus 4xh minus 3h. Let's go ahead and factor out an h. So you have h times 2h plus 4x minus 3 all over h. Those cross out. So here we go. It's time to bring in the notation again for the first derivative. The limit as h approaches 0 of 2h plus 4x minus 3. Plug in the 0 for h. That goes away. So you get just 4x minus 3. So that's the first derivative. So we need to do the same process. It'll be much faster, don't worry, for 4x minus 3 to find the second derivative. So the second derivative, or f double prime of x, the limit as h approaches 0 of, I'm going to go ahead and skip that equation part. So it's going to be 4 times x plus h minus 3 minus 4x minus 3 all over h. Distribute 4x plus 4h minus 3 minus 4x plus 3 all over h. So we can have 4x minus 4x is gone, negative 3 plus 3 is gone, so it's just going to be 4h over h, which crosses out to just be 4. So f double prime of x is the limit as h approaches 0 of 4, which we learned a long time ago, that if you have just a constant, that the constant is the answer. Okay, so the f double prime here of x is equal to 4. Okay, let's do one more. Same process that we just did, but to give you a little kind of sneak peek into the application here of derivatives, we're going to be looking at finding the acceleration using this position function for this particle. So as I mentioned before, the first derivative of a position function is showing your velocity, and the derivative of the velocity function gives you the acceleration. So finding the second derivative of the position function will find that acceleration. So let's find the first derivative. I guess we can just do it like this. So s prime of t. Again, I'm going to skip the writing the equation. We've been using it a lot now. So I'm going to start putting in my stuff. So 3 times t plus h squared. If you wanted to do all this with x plus h, that's fine. It doesn't really matter. You get the same stuff. T plus h plus 1 minus the original function, 3t squared minus 4t plus 1. Okay, that problem of before is still lurking around all over h. This will be much faster, don't worry. Let's see if we can distribute this a little bit more in our head. So if t squared times 3 is going to be 3t squared. 2th times 3 is going to be plus 6th, and then h squared times 3 would be plus 3h squared. Minus 4t minus 4h plus 1 minus 3t squared plus 4t minus 1. We're going to cross out a bunch of stuff. So we have 3t squared minus 3t squared gone. We have negative 4t, positive 4t is gone. What else? Is that it? There we go. 1 minus 1 is gone. Okay, so the only things I'm not crossing out are 3h squared plus 6th minus 4h all over h. Let's factor out an h. So it's going to be 3h plus 6t minus 4 all over h. Cross them out. Now we're ready. So s prime of t, again, this is finding the velocity. This is the first step. The limit as h approaches 0 of 3h plus 6t minus 4. Plugging in h, 0 for h, I should say. 3h is going to go to 0. So the answer is just 6t minus 4. So if you wanted the velocity function, it would be 6t minus 4. We need to find the derivative of 6t minus 4, and that will give us the acceleration. All right, so we have s double prime of t, which is, again, I'm going to skip the formula step. Limit as h approaches 0 of 6 times t plus h minus 4 minus 6t plus 4 all over h. So we have 6t plus 6h minus 4 minus 6t minus 4. Stuff's going to cross out. We have 6t minus 6t, negative 4, and that should have crossed out. What did I do wrong? Because you wrote positive 4 here, Douglas. 6t minus 4. Just a simple reminder, if you're watching this video, and I know not everyone does because we do this live in class, but if you're still watching this video and you saw what just happened there, right? I make mistakes all the time, guys. And I just take a moment like, okay, can I figure out my mistake? So don't be discouraged when you make mistakes. You actually should be encouraged because that's where your brain actually has the most chance to fire a new synapse and, kind of grow those pathways, if you will, in your brain. So it's actually a positive thing to make a mistake. Okay, so distributing the negative, I actually should have made that positive 4. Now those cross out. So we have 6h over 6h over h, which is going to just be 6. So s double prime of t is the limit as h approaches 0 of just 6, which we've talked about now many times. That'll just be equal to the constant 6. All right, throw some units on there since this is an application. We're talking about meters and seconds. All right, so this is going to be meters per second squared. Okay, that's the acceleration. All right, so again, thank you for bearing with me. I know there's a lot going on here, but hopefully you're ready to not find a derivative like that ever again. I'll show you the quick ways to do these rules, quicker ways to do this very soon.